Hello, friends. I recently realized how little I know about linear regression, while it being such a classical model that lays foundation for so many important statistical and machine learning efforts. So I decided to make a series of videos, and I would like to start by reviewing the assumptions it makes. There are actually 5 of them I want to talk about with you today. And of course, let's start with the linearity assumption. Linear regression assumes the output is linear in its parameters. We can call y a linear combination of x or a weighted sum of x, where the weights are proportional to the feature's importance. You may also notice that there is an error term, which represents the random noise in your data that provides no meaningful information, and whose assumptions we will talk about very soon. With the linearity assumption, a change in one variable will produce a linear change in the target, and the influences of multiple variables are additive, which gives linear regression great interpretability that not many machine learning models have. With this example linear function, to interpret feature x1, we can simply say, given all the other features constant, increase x1 by 1 unit increases y by 2 units. So how do I know if my data conforms to the linearity assumption? If you only have one variable, then a scatter plot will do. But if you have more variables, residual plot will usually be more helpful. Ideally, your residual plot should show no discernible pattern. You should see the data points systematically distributed around a horizontal line. If your residual plot exhibits a clear U-shape, for example, then it indicates that the model makes systematic errors whenever it's making large or small predictions. A non-random pattern like this supports a non-linear model. Or more simply, just take a look at your model's accuracy. R-squared measures the percentage of the variance in the dependent variable that your model explained, and the lower R-squared value shows a weaker linear relationship. Okay, so what can I do when I have non-linearity? First, you can try to apply non-linear transformations to current features and introduce them to the model as new features, such as polynomial regression. The linearity assumption only requires your parameters to be linear. Your independent variables can have as many nonlinear transformations as it needs. Also, you can add interaction terms of the current features if you think the effect of one variable depends on the value of another variable. Last but not least, it could also be that you have simply overlooked some important features, which you can add to the model. Linearity is the base assumption of linear regression and probably will have the most serious impact if violated. If after all the transformation, your data still doesn't have a clear linear relationship, then your predictions are likely to be seriously in error, especially when you extrapolate beyond the range of your sample data. In this case, linear regression simply does not have enough expressiveness to describe the more complicated relationship in the data, and you should probably consider applying a different model. The second assumption of linear regression is that there's no perfect multicollinearity among the features. An example of collinearity is feature 1 is how tall a person is, and feature 2 is how tall their mom is. Another example is when you create dummy encodings from a categorical feature and don't omit the base level. Note here that collinearity is not the same thing as the interaction we just talked about. Collinearity, or correlation, or association, talks about how variables influence each other's values, and it is only between the variables. While interaction talks about how variables interact in terms of their effect on a third or dependent variable. The effect of one of those variables on the dependent variable differs at different values of the other. For example, my mom's height has a big influence on how tall I grew up to be, but they don't necessarily impact on something together. Two fair coins are perfectly independent, but it is whether the two sides are the same or not affect the results of your bet. So we have established that whether two variables are associated says nothing about whether they interact. Likewise, if two variables interact, they may or may not be associated. Multicollinearity can actually be present in the model, as long as it is not perfect. When there is some multicollinearity, the accuracy of the coefficient estimates decreases, but they are still unbiased. However, even though the performance may not necessarily suffer, you definitely lose the interpretability. For very important features can be masked due to being collinear with another feature. But if there is strong or perfect multicollinearity, it can make fitting a linear regression model extremely difficult to even impossible. Because from the linearity assumption, we already know that the contributions of the features is additive. It will become very challenging to determine how much each feature separately contributes to the response if they are highly related to one another. For example, if two variables are perfectly collinear, when x1 increases by 1 unit, x2 increases by 2 units, and so we observe that y increases by 4 units. So should the relationship be y is 4 times x1, or y is 2 times x1 plus x2, or y is 6 times x1 minus x2? Intuitively, if you expect an independent variable to positively impact the output, but the estimate coefficient is negative, then it's very likely that some collinearity is happening. Statistically, to detect collinearity between two features, we can look at the correlation matrix. To find multicollinearity between 3 or more features, the variance inflation factor, or VIF metric, is usually used, which measures how much redundant information a variable provides. So the smaller the Pearson correlation value, or the VIF, is, the less multicollinearity. So if there is multicollinearity, what can you do? Generally, you can do 3 things. First is to drop one of the collinear variables, as it provides mostly redundant information. If you know how tall my mom is, you don't really need to know how tall I am. Or you can see if you can combine the collinear variables into a new variable. Say use the mean of my height and my mom's height as a new feature. You can also apply some dimension reduction techniques like PCA. So that is the non-perfect multicollinearity assumption. The first 2 assumptions form the basis of linear regression. Violating the linearity assumption means that it doesn't make sense to use linear regression in the first place. And having perfect multicollinearity makes it impossible to fit a linear regression model. The next 3 assumptions we will be looking into is actually not required by linear regression, but by ordinary least square, the method we usually use to estimate the coefficients. Given this set of 3 conditions, the OLS coefficient estimates are guaranteed to be the best linear unbiased estimator, or BLUE. It is proven by the Gauss-Markov theorem. Violating these 3 assumptions may generate incorrect or biased estimates, create wider or narrower confidence intervals for the estimates, or result in estimates with high variance. I'll see you in the second part of this video.